Thank you very much for this kind invitation. So this is work I've been doing with Abanov and Wigman, and that's hydrodynamics and effective field theories, and so I will go through a number of things that echo. Non hai perso niente. Okay, so that's so I'm going to go through a number of things, which is anomaly inflow. So remember what is anomaly inflow, which should be used, and then well-known bosonic theory of fermions in 1+1 dimensions, and then I go through hydrodynamics and how hydrodynamics, effective action of hydrodynamics can be written, including anomalies, and the main tool here is to use anomaly inflow. Okay, and so what is hydrodynamics? Well, it's a low energy theory. Okay, in a fluid phase, it's like an effective field theory in principle, but in fact, so far is a different subject. The main point is that the effective fields are the currents, okay? Currents. So you don't have a field that represents you a low energy, weakly interacting degree of freedom, effective degree of freedom at low energy. You don't have this. You have currents, okay? And so it has been dubbed non-particle field theory, because there is no actual particle, so you are agnostic about what the basic degrees of freedom are. This is a virtue, but also a problem, and so my point of view is precisely the same of this review. So I follow, and so you have a certain degree of universality, because you think that basically the local equilibrium, the theory is determined only by symmetries, by its symmetries, which may be reasonable or unreasonable, or I don't know. It's something like that. Statistical mechanics is entirely determined by the thermodynamics, which is maybe as excess. I don't know. So, but it's unclear. It's unclear if. Okay, anyhow, so there is this presumption that is a kind of theory of everything, but in fact in the literature there are many theories of everything, because there are many authors that they write different analysis of aerodynamics, and it looks a bit strange. Okay, so it's very old, it predates electromagnetism, but so it remains fully understood. And in principle, there are many applications to strongly interacting system. You know better than me, quark-gluon plasma, and topological phase of matter, cosmology, astrophysics. There is a relation with gravity, which has been pushed a lot, and so it's a semi-classical approach. Okay, you don't quantize it, or at least you quantize later, and you don't pretend to go beyond response to background and one-point function. So it's not really a theory. It's a limited theory, but because we know so little about non-perturbative physics in 4 dimensions, it's still a very valuable tool if we can bring somehow in the context of quantum field theory, where we know what we are doing, what we are actually doing. Okay, and so what will be the subject? My subject will try to bridge with effective field theory, but using new kinds of effective field theories, which are the topological phase of matter. Topological phase of matter, in condensed matter system, you have the occurrence of low energy theory, which is not the usual Landau-Ginzburg, but it's a gauge theory. So it's a topological gauge theory. So it's a very new fact that you have that the low energy theory is a gap phase, but with non-trivial global effects, which are described, for example, by Chen-Simon theory. Okay, And so typically in a phase of matter, it's very important that there is a bulk and boundary, because the bulk is topological, but the boundary is a real field theory, massless field theory. In general, is a fermionic field theory, which has full-fledged dynamics, okay? And so there is this interplay between boundary and bulk, which is very important. And because on the boundaries you have massless Fermi, you also have anomalies, okay? And these anomalies have a counterpart in the topological theory, as we shall see. And and topological theories are perfect than hydrodynamic theory, because there are no particles, okay? There are no local excitation that you could say there's a particle. There are just currents. Currents, and then you have dual gauge fields. So conserved currents and dual gauge fields. So that's it. If you want to say,
sorry. But
yes?
in actual hydrodynamics of like fluid, there are phonons, right? There are actually.
Yeah. So this is of course, this is a topological theory. But if you want, it is formulated in terms of currents.
No, I'm trying to say that hydrodynamics typically is not topological, because there
No,
are.
I know it's coming, but somehow the setting is the same. It is empty of local fluctuation, but the setting is in terms of currents, okay?
Oh, but let me again continue on this point. Correlation functions in topological theories do not depend on the distance.
Yes?
Is it true also of correlation function of the currents? Does it not depend on the distance in hydrodynamics?
No. We shall see. We shall see. No. I just want to say that from the technical point of view, it's not aerodynamic as you. My statement was misleading, if you want. There are some technical aspects of aerodynamics, but it's not aerodynamics. It's topological. Is not aerodynamics. Okay. So we will discuss the perfect fluid, which is also at zero temperature, and dynamics is described by pressure and density. And for this formulation, there is a Lagrangian. There's an action principle, which is known. So, and we exclude dissipative forces, and it is impossible to include temperature and entropy, but I will not discuss it now. So, and then we will show that 1 + 1 dimensional aerodynamics of the Euler fluid is equal to standard bosonic field theory of fermions, and that in 1 + 1 dimension. In 3 + 1, we shall implement the anomaly in this formulation, and then we will see that relation topological theory also suggests extension of hydrodynamics which are possible. Okay, let me start from an example for a very different subject, which is topological phase of matter, well known, which is the quantum effect. This is to illustrate anomaly in flow, if you don't know it already, okay? So the anomaly in flow is a flow of the anomaly from the bulk to the boundary, okay? So you have this situation, this is a topological phase. So so you imagine that you feel all the levels of a first Landau level, okay, which are these cyclotron orbits, okay? Then you can arrange them into circular orbits, like the layers of an onion, okay? And so this is a radial view of the droplet of electrons, and these points are the location of the orbits, which are exponentially located at different close nearby value of the radius. So all these wave functions build up a constant density in the bulk, which is this, okay? And there is a very big gap. You have a magnetic field very big, so the gap is very big, and you cannot excite. So this is at low energy. This is in the bulk. There are no excitations. Okay, and instead on the boundary you have a kind of Fermi surface, because you feel up to some chemical energy here, and then you have a small fluctuation at the boundary, which are actually one-dimensional. So you have that the fermions at the boundary make up a 1 + 1 dimensional relativistic field theory. So you with linearized energy around the Fermi surface, and so it's a chiral theory, because this this magnetic field breaks a time reversal. So they don't just have one mode and not the other, and so this is a chiral fermion, and so it has a chiral anomaly. Okay. So how do I describe this chiral anomaly? This chiral anomaly is just a manifestation of the Hall current. Okay. Because suppose I put an electric field which is along the boundary like this, and then you have an orthogonal radial current in 2+1 dimension that I represented by script j, okay, in this way. So this current moves, but then when it arrives at the boundary, where does it go? It becomes a non-conservation of the charge at the boundary, okay, which is the anomaly. Okay, so because on the boundary theory you have this excess of charge, okay, and so you can say that the anomaly of the boundary theory is compensated by a classical current in one extra dimension. Or if you want that the system bulk plus boundary conserve the charge, and the anomaly is just because you limit yourself to what happens on the boundary, okay. So this is the anomaly in flow, okay. And in formula, you see that this is the current which is given by an orthogonal electric field, okay? And this is just a formula that the flux of the current, the radial current, there should be a non-conservation of the charge. And from this, you read that non-conservation of the charge as the expected form of anomaly in 1+1 dimension, okay? These two indices now run from only on two values, okay? Another fact that is very well known is that this current is described by Chern-Simons theory. So Chern-Simons theory in the bulk, okay, has gives you by variation with respect to the background, a big A gives you a current which is the Hall current, okay. Okay. So you can say that the Chern-Simons theory is effective theory of this topological phase. And in fact, it's very important in topological phase of matter. Okay? Okay, so now we go to discuss the boundary theory. And the boundary theory can be described by a free boson. This is a well-known fact, okay, that is extremely used. And so this is a starting point for any kind of bosonic description of fermions, okay? And interesting fact is that you have a U1 symmetry, but in fact you have two currents. So one is the neutral current, okay, which is the vector current, and the other is the topological current, okay, which is axial. So I put a twiddle over J to say this is axial, okay, and without twiddle is vector, okay. So this is a bosonic theory, but has two charges, one vector, one axial, like a fermion, okay. Then this action you can couple two backgrounds is useful to put both a vector background and a fictitious axial background to see the response. Okay? And in fact it's not completely unphysical. You can realize in certain material as you can model some deformation of materials or some property of material with an axial vector, axial background, okay? And so this is a form of the currents, okay? Of the two currents in terms of the dynamical field theta, scalar field, and of the background, okay? So skip one. Yeah. So how do I get these currents from the flow, from the inflow? Okay. Well, the previous theory I showed you before was chiral. Now I have to combine chiral and anti-chiral, and so the topological theory is so-called BF theory, which is a sum of two Chern-Simons. And this way I realize a time reversal invariant thing. So I have two fields, not just one, and then I introduce also these auxiliary fields, which represent which are dynamic degrees of freedom, which represent the currents. So you want to represent the three-dimensional currents, conserved currents are as degrees of freedom. Your theory is written in terms of currents, okay? But instead of writing currents, you write a dual gauge field. So you have two currents, and then one is axial, the other is vector. So you use with two gauge fields, P and P twiddle, the dual, okay? And also use standard wedge product, for differential forms, and the wedge product is not written, okay? You understand that this is wedge product, okay? Because there are no indices. So, so if I solve the equation of motion of this theory, I see that P and P is expressed in terms of background of a scalar field, because all this together is a closed form, okay? And the same for this field. So that this solution of the equation of motion gives me two kind of scalar degrees of freedom, okay? Okay, if I integrate the action, I get the expected response, which is similar, is extension of Chern-Simons before, okay? And so by anomaly inflow, I see that these currents, when restricted on the boundary, they give me no conservation of the currents on the boundary. So this is three-dimensional current in the radial direction, okay, should correspond to the non-conservation of the two-dimensional current on the boundary. So I reproduce the anomalies, the expected anomalies of the bosonic theory. Okay, so this anomaly flow is useful not only because it gives you the value of the anomaly, but it also suggests you which variable to use for the bosonic theory. You see, you have this theta and psi field, okay, that naturally enter in this analysis, which is classical. And so let's continue this analysis. So from inflow, I got this formula for the currents, which are gauge invariant. From the bosonic theory, instead I had this, okay, the same field, and this other, which is not manifestly the same, but in fact it is the same if you rely on a self-duality. So the theory I showed you before, the boson has a self-duality, and so this psi is a dual field of this other. So somehow this comes with two topological currents, and in a theory you rely instead on the boundary, you realize it with the topological and the neutral current, but then you can also have the dual theory in which they switch the, okay? So you see that from the inflow, there is a suggestion of which variable to use to describe the boundary theory, okay? And so I have reproduced the bosonic theory, okay? And as I said, and a suggestion for the field to use, okay?
So but self-duality does require theta and psi to be compactified on a circle
Yes.
of fixed radius?
Yeah. This is the bosonic theory has to be compactified to describe fermion, okay? Yeah, and there is a particular radius which is a fermion, then you can have other radius to describe anyons, but it's not the point of this analysis. Anyons are not. So, continue. Okay, now we go to the hydrodynamics. So hydrodynamics, we will use this Lagrange, this action. So I use the Euler formulation of, because you know in hydrodynamics you can have a Lagrangian formulation and Euler. So I use the Euler. So I stay in one point fixed and I see the flow passing. Okay, that's a most natural, in my view, relation with field theory. And so there is a long story about this the dynamic and the possibility to obtain this. There is an Hamiltonian formulation of hydrodynamics, but it's also a Lagrangian formulation. Okay, and the Lagrangian formulation is the following. You have energy which depends on some current, and then you do a Lagrangian transform, and you introduce pressure P, and pressure P, and you introduce the dual variable which are momenta. Okay, so this rho is the density, mu is the chemical potential, P is pressure. Okay, so it's if you want, is a Lagrangian transform of the energy. and then this is moment of particles, which in relativistic case is just the chemical potential times the velocity, normalized velocity. This formulation is very simple. You see, the action is the pressure. But the point is that Euler dynamics is a constrained system. So that's a main problem that you face. So it's not an ordinary Lagrangian like in field theory, okay? So you cannot take, you have this variable, which are the moment of particle, moment of the fluid, but you cannot really do a variation. You cannot do a variation, free variation, okay? Because there are constraints. Because it's coming from the Euler equation. Euler equation has an Hamiltonian, but then this Hamiltonian has Casimir invariant, so you cannot invert the symplectic structure, and so this is a constrained system, okay? So, so what I can do? Well, I mean, not knowing what to do, I mean, and not knowing the literature of the past 40 years, let's say, or 30 years, like me, I can do a very simple thing. I can take a variation which is a diffeomorphism, because that will give me the stress tensor conservation, okay? We give the stress tensor conservation. And in fact, this equation for the stress tensor conservation is the same as the equation of motion. So that's certainly a good equation, okay? Maybe it's not the complete story, but it's a good equation, okay? So let me put it like this, okay? Then there is a lot of work done, especially by Carter, okay, here, but I don't want to enter. So it's reasonable to consider a variation. It's not a free variation of this momentum, okay? But a diffuse transformation is okay, because certainly you will produce a word identity which is correct in the theory, okay? So when you do this, you get this equation which is called Carter-Lipniarowitz equation, which is like this, okay? In terms of this current, which is the dual of is a Legendre dual of momentum, okay, like this. Now there is a surprising fact that this equation is not an equation of motion, but is a constraint. So it is valid, if it is valid for one current, it's valid for any current, because the point is this is a top form in 2 dimension. So if you impose a top form on a top form a constraint, then it means that top form has not rank 2 but a lower rank, and lower rank of a symmetry matrix is then goes down by 2, and so in fact the only possibility is that this two form is just a closed form, okay? And so in fact the solution is for any fluid, okay, the solution is that the momentum is given by a scalar particle. Okay? At this point, if I use, for example, for the pressure a quadratic expression in momenta, I reproduce the action. I reproduce the scalar boson theory, quadratic theory. I can put coupling to the external background, and so I have shown that Euler hydrodynamics in Lagrange with the Lagrangian is the same as the bosonic theory in 1 plus 1 dimension. Okay? Got it?
Why did you use a quadratic expression here for P?
Because that's a scale invariant, and it's okay with the massless theory. But because I discuss the massless boson, which represent a massless fermion. Okay, but in fact you can use whatever. This was just to show that it corresponds to what I know before. But in fact, this formulation is nice because you can also do non-relativistic fluids, or you can put whatever. Okay, and in fact the anomaly will not depend on the form of the pressure. We will see. So that formulation is very nice because of this. Okay, now we go to 4 dimension. So the action is the same. Am I going too fast? No? Grazie.
I mean, it's not a crime to end.
Huh?
it's not a crime to end ahead of time.
Okay, so okay, maybe now it's lower. Okay, now we go to 4 dimension, which is the interesting thing. Okay, so what's the point? The point was already addressed by collaborator earlier, and so the action is still the pressure. The equation of motion is the same formula of before that I can write in terms of forms like the interior product, okay, or contraction like this, okay. And so if this is true for a 2 form, I can is also true for the 4 form of this form, okay, of this type, okay. And so that implies that again you have a top form which obey a constraint. So it means that this top form is 0. So it's is in fact is automatic, is identically satisfied. So the equation of motion also in 4 dimension, the equation of motion is like a constraint, okay? So then at this point, this quantity you can see that as a dual of a current, of an axial current, okay? So you have this axial current made out of momenta of the fluid. Moment of the fluid is a conserved current, so it's conserved axial current, which is called elucidating current, which is very simple. You have vorticity, which is of the fluid, and then you project along the momentum of the fluid. So you have a vorticity vector, okay, and you project along the velocity, okay, and that gives you elucidity, okay. So you see that this is a bosonic theory. It has a current which is a neutral current, okay. It has a current, conserved current, has stress tense and everything, but it also has an axial current. So the idea, which was I think first said by Son and Surovska, but maybe also other, is that maybe this is the axial current, okay. So I have a bosonic theory and I have 2 currents. So it looks like that this is the axial current, okay? So then, okay, let me couple two backgrounds, and you find out that the coupling to the background is this one, okay? So because this is a polynomial of the background of the variables, which has the correct dimension, the correct parity, and so on, okay? And now I introduce a new variable, which is this pi, which would be the canonical momentum of the fluid instead of being the kinetic momentum p of before, okay? Because you have a thing, okay? At this point, you can compute, for example, the chiral current by variation with respect to the axial background. You get this expression, and then you work out with the equation of motion. You consider this as an equation of motion, okay, and you get that reproduce the anomaly, okay. Instead, from the neutral current, you get that the vector current has this piece, okay. Okay, so somehow you say, okay, I have a hydrodynamics. I identify what is the vector current and what is the axial current, and then I couple to background, I get anomaly, so I kind of am in business, okay? Well, it's not completely true, because there is in this anomaly there is a piece missing, okay? There is a piece missing, so this action is incomplete, and so what we did is to complete it, and the idea is to complete it is to use the anomaly inflow, okay? So because we know what are the anomalies, what is the Chern-Simon in 5 dimensions which reproduce the anomalies. This is a well-known technical aspect of anomalies. Okay, please.
I have a basic question. Can you go back a slide for me?
Yes.
Can you explain the top line here? I understood the first implication, but the second implication, why dp is 0, I don't quite understand. From saying that dp is 0.
Because this is 0, okay? This equation.
Yeah.
Okay. Then using this, you also prove this, because this is a derivative, you can act on the first piece and second piece. So-
Right, yeah.
And then you get this is a top form, which is constrained, okay? And so it has to be a 0 up to a closed form. No, not closed form. Exact form.
Oh,
Okay. The exact form, however, does not enter in the following discussion. You can put it, but it doesn't enter, for example, in computing the anomaly. There is an exact form, but you can take care of it. Okay. And anyhow does not change the anomalies. Okay.
thank you.
Because when you compute the anomaly, you apply again D, so it disappear. Okay, in the form of the current there are exact pair pieces, but in the anomaly disappear. Okay. Okay, so we know what is the five-dimensional theory, and the five-dimensional Chern-Simons theory. So it is a combination of two pieces, because you have to consider that anomaly for dimension is both time and p preserving. So, and then you know that A is a vector and A tilde is an axial vector. So then you see that you should have a polynomial of third order which has either one axial vector or three axial vector. Okay. So in fact, in the anomaly in four dimension there are two independent structures. Okay, so in general the fermion can have two independent parameters here, and I normalize one to one by removing factor of pi 4 pi square. Okay, and then I leave this other as a parameter for easy of presentation, and for a Dirac fermion is 1/3. Okay, so these two contributions correspond to the two diagrams, to the two triangular diagrams that you have in four dimension. Okay. Okay, so that is what I expect for the bulk of my topological theory, which by inflow produce the anomaly on a boundary four-dimensional theory. Okay, which is a Dirac fermion. Okay, I can also do the chiral fermion, but that's more complicated. I don't discuss here. Okay, so this is the ordinary time reversal fermion. Okay, okay, so it has this form. Then I invent a gauge field, which I call corresponding gauge field, dynamic gauge field that I call pi and pi tilde, such that they represent currents. Okay. And dynamical currents coupled to this gauge field, and when I integrate them out, okay, I get the response. Okay, so this is my topological theory in 5 dimensions, consistent with the expected anomaly. Okay. Now, if I have such a theory on the bulk, I have to check that there is a corresponding theory on the boundary, such that the sum of the two, with this variable I've been using, is gauge invariant. Okay, that it tells me that there is inflow from the bulk to the boundary. Okay, so the two go together. Okay, and so what I get this action on the boundary, which has a pressure, and these two terms which are necessary for gauge invariance consistent with this bulk. So there is a previous piece and a new piece which was missing. Okay, and then by this anomaly inflow, I also got that idea that I should use two degrees of freedom for the fluid. One is a vector momentum, and another is the axial momentum. Okay. So in principle, from this anomaly analysis, I would have a fluid which has two independent kind of components. A vector fluid and a vector current, vector momentum, a vector current, and axial current. Okay. So I know how to describe this theory, and it will appear in forthcoming publication, but for the time being, let me make a simplification. So, okay, I reduced to a single fluid, okay, a single type of fluid by choosing for this P twiddle the fact that is just a closed form, exact form, okay. And also I don't put this axial degrees of freedom into the dynamics, which is contained entirely in this pressure. Notice that these pieces here are diff invariant, okay? So they don't depend at all on the metric or nothing. Just they're topological, okay? So all the dynamic is here, and all the anomaly is here, and in fact the result of the anomaly is independent on the form of the pressure. So that's a manifest universality of the anomaly, okay? So I'm left with these two variables. So I have the pressure of before, the momentum of before, okay, which is expressed in terms of this canonical momentum minus the field, and this other object, which is the axial momentum, which is a kind of superfluid. So you could dub this theory as a chiral superfluid phase, okay? But the most important fact is that I need this, at least a scalar variable, pseudo-scalar variable here to have gauge invariance. So as a matter of fact, these variables are dictated by gauge invariance, okay? Because this is a momentum of the fluid, so it's gauge invariant object, okay? P and PT are gauge invariant object. So if I have a background, I should have a field which absorbs the gauge transformation, and the minimum I can have is this pseudo-scalar, okay? So then eventually I get to this action, which was the action proposed earlier by Banach and Wigner, plus addition, which is in red, okay? This 5-dimensional background piece is just to ensure that everything is gauge invariant.
But
Okay.
so, in
Yeah.
the absence of external fields, so this psi, there is this extra psi d pi term, so it's just some kind.
Yes, if you adapt this reproduce the constraint d pi equal to 0, which was one of the equation of motion I obtained before.
But the coefficient in front of this proportional to anomaly, or
This is proportional to anomaly,
and this
and also this, yes.
at this proportion.
Yeah, but the condition is the same. So it's always varying with respect to psi gives you d pi equal to 0, which is one of the equation of motion.
So, meaning that without external fields, this anomaly doesn't show up. Like anomaly doesn't have any consequences for
Yes, you need to have this additional degree of freedom.
But it only appears as a Lagrange multiplier.
It's a Lagrange multiplier in this minimal theory. If I put also inside the pressure, then it acquires the dynamics. But the point is that the minimal choice. So because of gauge invariance, you should have this. In fact, this is not a mystery. It's just the Vesumino field. Okay. So because you have an anomaly, then you have a Vesumino field. Okay, which is psi. So this is another way to see if you have an anomaly, you have either a 5-dimensional theory, which is topological theory, or you have a Vesumino action in the same dimension, but this Vesumino action introduces you additional degrees of freedom. Okay, you know this, right? So the point is that anomaly.
It just mute, like in the examples I'm familiar with, it's just extra term in the action, but it doesn't introduce new degrees of freedom.
Why not? So you imagine the low energy theory of pions.
Right. Yeah.
The pion is a degree of freedom.
Yeah, but pions are there without, like, the pions are there no matter what, and depending on the anomaly, you get Vesumino term with just extra interaction for these pions, but it doesn't introduce any new degree of freedom to pion Lagrangian.
Okay, but I tell you that fermionic aerodynamic was missing this degree of freedom.
But in what sense if I understood you correctly, it just imposes constraint which already present in the theory without anomaly.
Yes. Yes. But I can give it to it a dynamics by putting into the pressure.
Okay,
So
but at least in this example, it does nothing.
no, because I did a simplified thing just to because I want to get the anomaly. Anomaly I will get for any dynamics, including zero dynamics. Okay. So, but I can do. So it is written here. So I can add a dynamics to psi, and I also can model chiral breaking. For example, you put here a term will depend on psi and not on the derivative of psi, and then you break chiral symmetry, and in a sense, you know, the new thing is that normally you can model an axial chemical potential by this by the potential of this axial field. Okay, so I simply say that this is not a gauge invariant object. You have to consider a combination with this pseudoscalar object.
But your claim that in general, anomaly implies additional hydra mode in addition to
Yes.
to phonons. If I talk about just perfect, like in the Son and Surovka context, they were just discussing normal fluid and saying that at high order, if anomaly kind of leads to some new effects, but they're not saying that there are new wave modes present in this
I
field.
mean, unfortunately, it is necessary for from very basic thing, which is gauge invariance. So you know, if let's talk about pion physics, okay?
Yeah.
Pion represent the anomaly of ultraviolet fermions.
No, well, pi match anomaly. If you start with pi and Lagrangian, and to match anomaly of UV theory, you add Vesumin-Witten term with appropriate coefficient. But that coefficient can be zero if there is no chiral anomaly in the UV theory, right? But we can have Goldstone.
Okay, but put yourself in the position that you know ultraviolet theory, you don't know pion theory. From anomaly inflow, you know that there should get some degrees of freedom that absorb the anomaly.
No.
And then you see, oh, right, I have to put pions.
Well,
So
but here
you know that there exist pions because they have to
I
match.
understand. Well, it's
Yeah.
either symmetry. An anomaly implies either symmetry is spontaneously broken, or there are massless modes. Like there should be massless modes which match the anomaly.
Yes.
But in this case, well, as you say, psi, the fact that whether it's dynamical or not, it's model dependent, right? It's not follows from anomalies.
No, the anomaly is true independence of dynamics.
Yes.
Including zero dynamics. Here you see explicitly. So you see? So in whatever I put like dynamics, which is in this pressure term,
Right.
I will get the same equation or the same anomaly. So even I mean free or undetermined scalar field would work.
So that means it's possible to match anomaly without introducing any extra mode. Like,
No.
No, why? Because anomaly doesn't force you to put psi in terms of p, right? You can.
No, it forces you. I told you. By anomaly inflow, you should have a degree of freedom which absorbs the anomaly.
Okay, but why is it in P?
Because it comes out of the form of the action. It's coming from this formulation. You have to see. Okay, so I told you the most general theory has two fluids. Okay, this two fluids theory is then you can treat in different way. For example, you can say that the fluids have different quantum conserved quantity, but somehow they move together. This is called entrapment, which is not.
But anomaly per se doesn't force you to have. You can match anomaly with just one fluid, as your action showed, right? So anomaly.
Yeah, one fluid, but with an extra pseudoscalar.
Well, but that pseudoscalar in the action which you wrote, it can be integrated out. It's just Lagrange multiplier, right? So it's not. There is no extra IR mode associated with that. Right?
Yeah, it's not a dynamical degree of freedom.
Right.
Just-
You can make it dynamical if
Well, you
want.
can make it, but you're not. Anomaly doesn't tell you that you need to make it dynamical, right? can
Okay,
match
maybe
anomaly.
maybe it's just a matter of words.
Well, I mean,
I'm discussing anomalous theory, okay?
Yeah.
So if there is no anomaly, it could be bosonic, so I don't need this degree of freedom. So I consider a theory which is ultraviolet as an anomaly.
Yes,
Then I tell you that if you go into infrared, you should have this extra degree of freedom.
but it's not a degree of freedom, right? As you told yourself.
It is a degree of freedom as a kinematic property, then you can give it to it a dynamics, and actually whatever dynamics you give to it, you produce the same anomaly.
Yeah, so that means anomaly doesn't force you to give it the dynamics. If you can keep it as a Lagrange multiplier, there is no degree of freedom from physical perspective, right? So it's
degree of freedom is ideal degree of freedom, so it should be one of the canonical variables in the Hamiltonian dynamics. It should be something that has a P and
But
a-
this is problematic in this formulation. It's problematic to say.
I mean, would you call the lapse or the shift in general relativity a degree of freedom? It's not, right? It appears nowhere. They give constraints and then they go away. and-
Okay, so so we have a discussion of what is the meaning of degree of freedom. Okay, so you have a kind of looser definition of degree of freedom.
So for me, degree of freedom is, you have a symplectic form. In this symplectic form, you have variables. If the symplectic form is invertible, right, it's non-degenerate, those are degrees of freedom.
But this
You're right.
reasoning in quantum field theory. Here we are kind
No,
of.
I'm talking about classical
primitive-
mechanics. I'm talking like Arnold. I don't know what is H bar, zero. There is a
No,
symplectic form in classical mechanics, right? We
Yeah.
agree on that. The
Here-
symplectic form is defined on a symplectic manifold.
Yes.
A symplectic manifold is well defined when the symplectic form is invertible. Otherwise,
Yes.
you have to go
Yes.
to submanifold. But those you can call the degrees of freedom in classical mechanics.
Okay. Okay.
And then you can also add other stuff like Lagrange multipliers that constrain your manifold. Right?
Okay, okay. So maybe I keep other degrees of freedom for the fluid for the two fluid theory that it don't exist. I know how to treat it very well now, but I will not discuss in this talk because I have to discuss how you treat a theory which has both a 5-dimensional and 4-dimensional Lagrangian. So yeah, the point is to discuss about Poisson structure, symplectic structure here is more murky because of this constraint in hydrodynamics. So we should be maybe less. We should be kind of more general. Okay. So
But if I remember right, because originally my question was motivated. If I remember right, Son and Surovka, as a consequence of anomaly, had a non-trivial effect even without external fields. There was contribution to, I think, some
to the chiral magnetic effect.
Right.
Yeah.
Well, even without external.
Yes,
external
I can reproduce from this.
Well, yeah, that's fine, because that I don't see, right? Because in this theory, if A tilde is equal to 0, then it looks like psi just imposes the.
No, but you have to put you have to put it here. You have to put into the pressure. Then it will become dynamic, and then.
But you said that that's not forced by anomaly.
No.
But for Son and Surovka, that effect was a consequence of anomaly. Here, it's kind of you can put it, but you don't need to put it there. That's my confusion.
This is not true. I mean, I use this. I have done the calculation of chiral magnetic effect with this action, and this psi is important because when you have to do the chiral magnetic effect, you need to put this. Oh dear, what's happened?
You've gone to sleep.
Sleep. Sorry. First let me
unitary mode that blacks out the screen. Like sometimes that happens. Like,
Hmm?
I think that is, oh, yeah. But this is the projector.
No, the projection is fine, I think. It's just.
But it's not, it looks like
Oh,
Yeah, it looks like the projector is off.
No, it's disconnected.
Sorry, we took a discussion, took too much. Okay, now it's fine.
It's probably the last.
Jesus. I have to restart the laptop. So sorry, I have to restart the laptop. Went to a mess. Oh, it's coming. Yeah, so what I wanted to say is that the chiral magnetic effect is J equal to PdA, okay?
I think
Yes?
there's also, that involves external field. There's also
Yes.
what they call chiral vertical.
Exactly,
vertical effect.
yes.
That's-
PdP, okay?
Mhm.
Okay, so this you need this P, okay? And if you have so this usually you say P is mu theta, which is chiral thing, okay? And so this is mu tilde B plus d omega, okay? Which is chiral magnetic effect and chiral vertical effect, okay? Great. So I can get this result when in the previous theory when I have two fluids, okay, P and P tilde, which is okay. So you get this thing, okay. Instead, if I go this to simplify